Hi there everyone, Augie Kennedy here with the last actual lecture of Super Awesome Calculus Calc 1. I don't know if there will be a Calc 2, we'll have to see if anybody actually watches these. But, alright, last time we talked about volumes by cylindrical shells. Now today, the last chapter of Integral Applications of Integrals, we're going to skip section 6.4 that James Stewart dictates gives to the Newton's concept of work, and instead we're going to talk about the average value of a function. Work is something that you'll discuss in physics, should you take that, and I just feel like this is a better thing to examine. So, average value of a function. But before we go to the average value of a function, let's go ahead and let's look at the big problem from last time, which was on volumes by cylindrical shells. So, the question I asked you to use cylindrical shells method to find the volume of y equals x cubed, y equals 0, and x equals 1 around y equals 1. Okay? So the first thing that you'd want to do in this situation, as you know, is you'd want to graph. This is a very easy graph. These are very easy functions. So let's go ahead and plug them in. We've got x cubed, looks like that. X equals 1, looks like that. Y equals 1, looks like that. That's what we're going to revolve around. And y equals 0 is that. So really we've got this little sliver in here. And if we magnify it, so you can see what I mean, there's x cubed, there's x equals 1, sure, there's y equals 1. So we got this nice little area, a thunderstorm already. Well, we're going to beat the thunderstorm. Alright, so we want to flip. How are we going to flip? Well, first of all, we know this is y equals 1. So, and we also know that if we're going to take a cylindrical shell of something that looks like this, we'll probably want to take a dy integral because the shell itself, if it's rotated, is going to be like that. And it's just going to be easier to take a shell like this around dy and basically use a dy integral. Now, as you might remember, we can't use just the function as the radius here because we're rotating around y equals 1. So instead, we've got the radius, or the height, well, hold on, radius is going to be 1 minus y. Right, but the height is going to be 1 minus the cubed root of y. Why? Well, because we got to go x, we got to solve, if it's a dy integral, we have to solve this in terms of x. So x equals cubed root of y if y equals x cubed. Simple enough. So now we're ready for some formula. Let's go ahead and let's plug it into the volumes of cylindrical shells formula, which we have volume equals 2 pi x f of x dx a to b. Alright, well, that's the same as volume equals 2 pi 1 minus y 1 minus cubed root of y dy. We know what x is. We know what x from the original function. So basically we just set everything in terms of y. Now, as far as the bounds are considered, this is really easy to see. We're dealing with cubed root of y and we're dealing with 1, and they're going to intersect, and they're going to intersect at 0 and 1. We can see that from the graph. So we're going to be examining the integral between 0 and 1. Now, that would make the volume equal to 2 pi times the integral from 0 to 1. We're going to distribute. We're going to go ahead and do the multiplication here to expand this. To 1 minus y to the 1/3 plus y to the 4/3 dy, which is the same as 2 pi times y minus y squared over 2, fundamental theorem of calculus right here going on, minus 3/4 y to the 4/3, remember, add the 1, so that would make this plus y to the 7/3 over, well, 7/3, so 3/7 times this quantity. Alright, and we're going to evaluate that between 1 and 0. And if you were to do that, you'd find that the 0 doesn't actually come out to anything. So we're just going based on 1, and plugging in 1 and multiplying by 2 pi, you're going to get 2 pi times 5/28, which is the same as 5 pi 14th is the volume. And there you go. Pretty cool. So, on to average value of a function. Today's concept is actually really, really simple. Like really simple. Basically, when we want to figure out the average of something, now this is going to potentially come in fairly handy in statistics should you ultimately take a statistics class. But we know how to find the average. If you've got a set of numbers here, 1, 5, 10, well, let's make this even easier, 5, 10, 15. You've got to find the average of these numbers. Well, what would you do? Well, you'd add them, and then you divide by how many there are. So we add these together, we get 30 divided by 3 is 10. That's how you find an average. I'm sure you already knew that. Add together divided by the number. But what happens if we have a function and we want to find the average of it? Let's say we've got an f of x equals x squared between 0 and 4. I mean, we know what the graph of that is going to look like. Between 0 and 4, it's going to be the parabola. But what exactly is the average of that function? Like, where is it in average? Well, there's actually a really simple formula that we're not going to prove. But it's a pretty simple formula that will show you how to find the average value of just about any function. And it is this. The average value of a function, fave, hold on, f average, that's how it's written, equals 1 over b minus a, that's 1 over the upper limit minus the lower limit, of the integral from a to b, f of x dx. Isn't that simple? I think it is. So let's go ahead and do that. Let's find the average of x squared on the interval 0 to 4. Alright? Well, that's going to be the same as 0, of course, in this case would be a. 4 in this case would be b. And f of x, of course, is x squared. So, 1/4 times 0 to 4 x squared dx. And using the fundamental theorem of calculus, we know that's just going to be 1/4 times 0 x cubed over 3 evaluated at 4 and 0. We know that 0 evaluated there won't be anything. What about 4? Well, 4 times 4 is 16 times 4 is 64. So, 1/4 of 64, which is 16. So, it comes out to 16 after all. Yeah? Yeah. I didn't know that, but that's good to know. So the average value of that function between that interval is 16. Alright. So that's the average value of a function. Now, if you may remember, we had that fun question a while back. Well, I mean, you might not have thought it was as fun as I did. I thought it was a pretty fun question about the monk who leaves his monastery and walks up and then walks back. We use the mean value theorem for that. Well, now we have the mean value theorem for integrals. Once again, I'm not going to prove this thing. The book does, it does a job. It does a job of proving it. But it's pretty easy to see how this works and why this makes sense. So, we have the MVT, mean value theorem, for integrals. Okay? And it basically says that if f is continuous on the closed interval a to b, then there is a number c in that closed interval such that f of c is going to be the average 1 over b minus a to b, f of x dx, or concordantly written, that's the same as saying that a to b, fx dx, if you distribute through, is simply f of c b minus a. So that's basically the mean value theorem for integrals. It makes total sense. It just says that there's going to be an average, and it's going to be a number in between that interval. So, there you go. I don't really see any need to belabor the point. Go ahead and try it, and if you get a creative application for it, go ahead and use it. Now, today there's not going to be a big problem. No big problem for today. That's because this information is going to be covered on the test, which is the next lecture. It's going to be our last test. So, go ahead, find some functions that you happen to like, pick some random intervals, and go ahead and see if you can find the average values of those functions. Otherwise, if you don't take the test, it's been an absolute pleasure making these videos, and I really hope that you've been able to derive some utility out of them. I know it's kind of made my summer go a little bit less slowly. So thanks for stopping by, and y'all take care.